But the funny fact is, when your high school teachers taught you this and forced you to remember this, they didn't spend time to explain the basic properties of magnetic field. Okay. Or I can even cast a challenge. Does anyone here know the difference between magnetic flux density and magnetic field intensity? So in the past, we encountered magnetic field. We understood the vector field quantity B, but B is actually called the flux density of the magnetic field. So think hard. How did I introduce E field to you? When we talked about E fields, when discussing the two fundamental postulates, we introduced divergence of E is equal to rho. And this E is the E field intensity. And when we have materials, then we introduced D, right? Then we introduced D, which is the flux density. But up front, now moving into magnetic field, we are introducing up front B as the flux density. Okay? So that is one thing already different. It's already different. So after today, I hope I can convince you electric field and magnetic field, they are by default very different. Okay? Okay. Take a look. Right? B. This is flux density. Okay? As compared to E field, we introduced the E field intensity. Okay? Now, before I move to the PowerPoint again, let's review. Your examination's coming up anyhow. Let's do a quick review. Divergence of E is equal to rho. Rho is the charge density, right? This is fundamental postulate 1. And then the second postulate tells you curl of E is 0. So you should be asking yourselves, what are these two postulates telling you? What kind of message are they telling you? The first equation is called Gauss's law. It's actually telling you, well, if you want to have some E field in space, you have to have charge, right? You have to have charge to produce the E field patterns. That's a message of the first fundamental postulate is telling you. What about the second one? Curl of this given vector field is always 0. What does that tell you? This postulate is telling you if you have a curl-free vector field, then this field quantity is a conserved field, 保守场. And at the same time, it is telling you this field looks like a radiant field if you have only a single charge. So together, combining these two, I showed you repeatedly, if we have a single charged particle, then the field lines are radiant. Right? It's radiant everywhere in a three-dimensional way. So actually you have a three-dimensional sphere, like the sun. Okay? All right. So whenever we look, if we want to understand about the field quantity, we look at the fundamental postulate. Basically, the fundamental postulates are telling you basically everything. Okay? And that is why the fundamental postulates are so important. As a direct comparison, for magnetic fields, the flux density has a zero divergence. Now you have to think very hard. What does that mean in a physical sense, in a way that you can understand? A vector field, the magnetic field is also a vector field, but its divergence is always zero. Let me just try to write it for you, right? Side by side. Divergence of B is equal to 0. Let me erase this one. It's too annoying. You compare side by side. E field, you take this divergence, it's non-zero. But for B field, the magnetic field flux density, you take its divergence, it's always 0. So right at this moment, are you able to tell yourselves what type of field is B? Well, you might not be able to tell, but let's follow the discussion, right? For E field, divergence is not equal to 0, which means if you have charge, single charge, multiple charges, doesn't matter, as long as you have charges or charge in space, you have E field. So another way to appreciate Gauss's law is the source to create E field is charge. Now what about this? This fundamental postulate is telling you divergence of B is equal to 0. What does it say? What's the physical meaning of that simple equation? It is effectively telling you, hey, in the real world, I mean, at least in the conventional world, we don't have a corresponding single element, basic element that can create magnetic field. Okay? Basically, there is no so-called magnetic source or a single particle that can give rise to magnetic field. Okay? So the difference between E field and M field is so dramatic. Electric field, you can easily isolate a single charge, so you know it produces E fields. But for magnetic field, you don't have a well-isolated source. You don't have a single particle which acts as a source to generate magnetic field, because divergence of B is equal to 0. Okay? So that's an underlying physics being told by this simple postulate. Right? You don't have a simple isolated magnetic source. In differential form, you have divergence. Divergence is always associated with the volume integration. But then once you have volume integration, you can invoke divergence theorem to have a closed surface integration of that field. So the same postulate, but formulated in the integral form, is the B field. If you have B fields in space, and you use a closed surface, and you try to evaluate the resulting field quantity over the entire surface, it's always 0. Now, what does that tell you? The same postulate, but written in the differential form, tells you, well, there's no isolated source to create magnetic field. But in the integration form, this is telling you another message. A quite shocking message. If you cannot come up with a right picture now, let's come back to the E field. In E field, right, divergence of E is equal to rho. So if you calculate over a closed surface, D dot ds is equal to the charge, right? So the simplest closed surface we like to form in three-dimensional space is a sphere. Right? So in this case, this is telling you, well, if I evaluate the closed surface integration of the E field over this sphere, I have the amount of charge enclosed in that sphere. But this is telling you, each location on the surface, you have field line penetrating across the unit differential area, right? So basically, divergence of E is not equal to 0 means you have field lines penetrating or crosses the differential surface. But now the fact that B making a closed surface integration is always 0, always 0. Are you able to come up with the distribution or the shape of some B field lines by looking at this or try understanding this formula? Well, I can again form a three-dimensional surface. It's a sphere, right, with a radius of r. Spherical surface. I form any type of surface, and I do have B fields, but the result is the surface integration is always 0. What does that mean? That means magnetic field lines, well, close upon themselves. Take a good look. E field lines starts from the positive charge and terminates on the negative charge. So it's radiant. It's unidirectional, right? Unidirectional. Therefore, if the surface contains or encompasses a charge, you will have non-zero fields flowing out across the surface. Magnetic field, the field lines closes upon itself, right? For this field line, it's completely encompassed within the sphere. So basically, there's no penetration across the surface, right? Therefore, the surface integration goes to 0 because that field line is contained within the sphere. But the second case is, well, if the field line of the magnetic field is a very big loop, it's a very big loop. This field loop is bigger than your surface, but you have one going up, one going down, one going down, one going up, right? So basically, the net flux of this big closed loop magnetic field line is still 0. Now, as a summarizing statement, closed surface integration of B is always equal to 0 actually tells you the magnetic flux lines, the flux lines form closed loops. Right? So this is something I really want to nurture you, looking at simple equations, but you should be able to come up with very practical and conceivable physical pictures. So you should be able to draw out the resulting field profiles. All right? So in that process, you learn, you understand, so you are not memorizing. All right? Second postulate. Curl of B is equal to the vacuum permeability. This is permeability, okay, as compared to epsilon 0, which is permittivity. In magnetism, we have some constant called permeability. And J is something we just learned, the current density. Okay? Simple enough. Let's go back to the blackboard. I like to have side-by-side comparisons. For E field, curl of E is equal to 0, right? But now, curl of B is equal to non-zero quantity, mu 0 J. Side by side, once again, you can see the dramatic difference between the two field quantities. One field quantity, E field, is having a non-zero divergence but a 0 curl. Magnetic field is having 0 divergence but non-zero curl. So this is really, really different. Right? It's just like two twin brothers or sisters, but who have very dramatic personalities. Okay? All right, so let me ask you a simple question. From the E field postulates, we concluded the E fields for a single charge is radiant, and I also said, therefore, the E field, curl of E is equal to 0 means, physically, E fields are conserved fields. Now, such a nice teacher, I already gave you the answers, right? Now we move on to magnetic field. Curl of B is not equal to 0. What does it mean? The second postulate also contains a lot of information. By dramatic comparison, right? Direct comparison and dramatically different, you should be able to address me without any doubt. Well, since curl of a vector now it's non-zero, this field must be non-conservative. And what do we call a non-conservative vector field? Go back and check. I actually covered this in vector analysis. If a given vector has a non-zero curl, then this field has closed loop forms and therefore represents a vortex field, 漩涡场. Go back and check. We actually went over this in the past. Okay? So the second postulate for magnetic flux density is telling you directly up front, hey, this field is a vortex field. It is non-conserved. That is message number one. There is another message. What is the second message? I invite you to come back to the blackboard. The filming crews are very overworked. For each field quantity, if we want to understand it, we want to understand in its profile, its pattern, and how it is being generated. So for E field, the reason you can have E field is you have charge, right? If you have charge, you can create E field. But for the first fundamental postulate of magnetic field, up to now, we only concluded there is no isolated source to produce magnetic field. So even though this first fundamental postulate is telling you how the field lines look like, but it does not tell you how the field loops are generated. And that piece of missing information is covered here. So now, please tell me, how can you generate this non-conserved vortex magnetic field? If you have current density, or meaning current, then you have the ability, you have the chance to generate the vortex magnetic field. All right? So this is telling you, well, as compared to E field, where you have stationary charge, if you want to create magnetic field, you must have moving charges, right? Moving charges give you current. So you must have current in order to have magnetic field. And that is the reason why we introduce magnetic field directly after discussing static electric current. You need to understand about current in order to understand about magnetic field. Okay? So current, so again, let's come back to the assumptions. For steady state electric current, we assumed we have constantly flowing charges to give you conduction current. But at the same time, do you still remember what is the assumption? We only have the current, but there's nothing else. In that space, we only have current and maybe we have E field, but we neglected magnetic field. But now you know it's impossible. Why? Once you have current, you have magnetic field. Okay? This might be shocking. As I said long time ago, all the basic assumptions when we covered static E field, steady state current are probably non-practical. Okay? You have two charges, they either repel or they attract each other. How can you keep the space, keep the distance, right? So reality are very complicated, but you have to understand them from the beginning in simple situations where you make huge assumptions. So now the real world is once you have current, you have magnetic field. And J equals sigma E. So basically in our world, we have E field, we have current, we have magnetic field all together at the same time. That's the truth. Okay? Okay. Curl of B is equal to the vacuum permeability times the current density. This is written in the differential form. Oh, whenever you see divergence of curl, it's differentiation. We can also use Stokes theorem to have a line integration over a closed loop is the amount of current encompassed by that loop. So look at it again, and at the same time, I'm going to reproduce that on the blackboard. Let me reproduce it on the blackboard. This equation is telling you, well, if I really form a closed loop, right? This is my C. If this closed loop is having some current being enclosed inside it, then at or on this closed loop, I must have some kind of magnetic field lines, right? So in this situation, I have to ask you to pay particular attention to the directions of the field and the current. So right now, I'm trying to express, I have current flowing out into your eyes, okay? So we have to follow the right-hand rule. So when we perform the curl, and thus the curl direction conforms to the direction of the B field, right? So when your four fingers are moving along this closed loop, the thumb points into the direction of your current. And that is the correct direction of the B field, right? So in this case, the B field is counterclockwise, 逆时钟, okay? So again, I'm showing you the B field lines form closed loop upon itself, and then when you have B fields, you encompass some kind of current. So basic current is the fundamental element that can generate magnetic field lines, okay? But to maintain a steady current itself is very deep, right? As we talked about, if we want to maintain a steady state electric current, we need to have a non-conserved source, a battery, current source, voltage source. They are itself non-conserved. And therefore, that non-conserved source could generate non-conserved field. All right? So this is known as the Ampere's circuital law. The circulation of magnetic flux density can be used to determine how much current is being encompassed in that closed loop. So that is called the Ampere's circuital law. All right? So let me stop here. Next Monday, we're going to continue to understand, and we are going to use this Ampere's circuital law extensively. All right, thank you.